Good afternoon. We're just waiting for some more folks to join. We'll be with you shortly. Welcome to the webinar on air conditioning applications. Good afternoon. Thank you for joining us for the AHRI Refrigerant webinar series. We'll be discussing some significant volume of research that's been completed around the transition to low global warming potential refrigerants. Welcome to webinar 1. This is the air conditioning applications webinar. I'd like to introduce our panelists this afternoon. Tom Watson will introduce this particular webinar. He's an engineering consultant for Daikin Applied and a member of the AHRI Research and Technology Committee. He's the chair of the Flammable Refrigerant Subcommittee of the Research and Technology Committee that is conducting research on the use of flammable refrigerants. Next, I'd like to introduce our second speaker, who is George Hunter, who works as an engineer within UL's Research and Development Organization. He's been the lead investigator in AHRI's 9007-1 and 2 projects dealing with flammable refrigerants, and he's the current lead for AHRI Project 8028, A2L refrigerants and firefighter tactical considerations. Then we'll be speaking with Dutch Usselton as well as Rusty Tharp. Dutch is a retired mechanical engineer fellow from Lennox International and an ASHRAE fellow. He has been active in several of the AHRTI A2L refrigerant research projects. And I think that's an understatement to describe all the work that Dutch has done for this industry. Rusty works for Goodman and has been in the industry for over 3 decades. He's heavily involved in AHRI, the Safe Refrigerant Transition Task Force, as well as the Flammable Refrigerant Research work. He's the chair of ASHRAE Standard 15 Committee and a member of UL STP for 60335-2-40 and participates in the international standard setting activity. We'll then be hearing from Vero Patel, who is an R&D associate staff member in the Building Equipment Research Group at Oak Ridge National Laboratory. His area of expertise is in experimental thermal and fluid sciences, and his current research involves new and improved types of energy-efficient building equipment with specific applications in HVAC-R that use A2L flammable refrigerants. He has recently completed an extensive assessment of flammable refrigerant leaks from building HVAC equipment as part of the AHRTI Project 9012 and extension. Finally, we'll be hearing from Dick Lord. Dick works for Carrier Corporation and has for 47 years and is a senior Carrier Fellow in the Advanced Technologies and Refrigerants Group, as well as an ASHRAE Fellow. He's a member of the UL 60335-2-40 3rd edition and 4th edition working groups and is a consultant to the ASHRAE 15 and ASHRAE 15.2 committee. He's also a member of the AHRI Safe Refrigerant Transition Task Force. He's actually a co-chair and has been involved in many of the AHRTI research projects. Welcome to all of you, and thank you so much for taking the time to present and share this information with folks today. And with that, I'm going to turn this over to Tom Watson to introduce this first session.
Well, welcome again to everyone. And I just want to first thank all the great sponsors we have. This has been a collaborative research program conducted through AHRTI, which is a open public resource research that anybody can participate in throughout the world. So we have ASHRAE as a sponsor as well as AHRI. California Air Resources Board and the U.S. Department of Energy has been a great contributor as well. And our objective was to produce public available technical results to support code and standard activities related to the use of flammable refrigerants. And on the next slide, we'll talk about our priorities were to support standards development with testing. And initially we went out and surveyed every standards activity organization that we could find throughout the world. And this is well over 100. And looked at the missing information gaps and also looking for overlaps. So where things really weren't needed. So then we developed testing and test conditions that we wanted to simulate actual applications. We really want to educate standards users and enforcement of personnel. And we're addressing key elements: ignition event severity, charge quantity, refrigerant sensors, and mitigation techniques. So on to the next one. We have a webinar series and you're attending the first one, which is today. In the 30th, 1 week from now, we have commercial refrigerant applications. October 7th, understanding refrigerant sensors. The 14th of October, predictive tools for refrigerant behaviors. And on the 25th, the final one is refrigerant ignition in open flames, hot surfaces. Has anything fundamentally changed? So welcome to the first seminar. And we'll go forward. And again, I want to thank all the speakers and the collaborating organizations. With that, I'll turn it over to our speakers. Thank you.
Good day, everyone. I'm Dutch Usselton from Linux. I was given the opportunity to provide a few remarks that are really providing context for this research project 9007. And it's important for me to say that the work that was done on this project, it was a big, expensive project. There was also, in addition to air conditioning equipment, there was refrigeration equipment that was tested, but we won't be going over those results today because this seminar is focused on air conditioning. So I'm not sure, we probably have a very broad audience, and I don't want to assume that everyone knows all this stuff. Many of you probably do. We started looking into lower global warming potential refrigerants quite a long time ago. As a good way to give you an indication, we already had a significant research program going in 2011 for looking at the performance of different candidate refrigerants. So we've been looking at the performance side for longer than that. We also need to make sure that people understand we didn't just consider flammable refrigerants. You know, we would all actually rather not use flammable refrigerants. But for the air conditioning sector, that seems, at least right now, where we're at, and there's reasons for that. We talk about volumetric capacity. That's the amount of volume that needs to be pumped by the compressor to do the air conditioning job. And unfortunately, there's a relationship between low GWP, volumetric capacity, and flammability. And for our applications, I'm talking factory air conditioning. We need a high volumetric capacity. It's not possible to run with 2-inch suction lines and compressors that are, you know, half as big as a 55-gallon drum. We can't really do GWP refrigerants that have high volumetric capacity are flammable. And so there's a chart I'll show you in a minute that shows you what we were looking at back in 2011. Another thing I wanted to make sure everyone understands is that it's very important for us to maintain system efficiency. The reason is pretty simple. Our equipment runs off of electricity, and in the United States, a significant portion of the electricity that's generated comes from fossil fuels. So if in the effort to reduce the GWP of the refrigerant, we actually go backwards on efficiency, what we're doing is shifting the problem so that the power plants emit more carbon. So I think everyone that's been working on this problem, you know, is in agreement that we can't really go backwards in efficiency. So that's kind of a cut for some refrigerants. And we're looking for alternatives to R410A, which is a mixture of R32 and R125. In fact, the reason for the R125 is because it acts as a fire suppressant. So R32 is actually flammable, but with a mixture of R125, it isn't. And another characteristic of that combination is that there's not a big problem of fractionation between those two refrigerants. So in a way, that's another cut that we have is refrigerant mixtures. If they fractionate strongly, then they're not really suitable in an air conditioning system. Okay, so here's that chart. And I just went back in my computer and tried to find some documentation back in the early days. The AHRI project was to look at performance. And going down on the left side, 134A, that's an air conditioning refrigeration refrigerant. 404A is also. 410A is the predominant air conditioning refrigerant, although it's sometimes used in some refrigeration applications. And then 22407C, well, 22 is not allowed anymore, but that's not for air conditioning. So what you see, A1 is the first column where you've got candidate refrigerants, and we didn't have any A1, which is non-toxic, non-flammable candidates that we had been able to identify. So that's why we're over in the next column, A2L. Okay, next slide. So a new category was created in the AHRI system, 2L. It's for refrigerants that are flammable, but they have a low burning velocity and high minimum ignition energy, which means it takes a strong ignition source to ignite them. The burning velocity relates to how fast the flame spreads. And to give you an idea, we're looking at refrigerants with flame spread less than 10 centimeters per second. So that's pretty slow. It's so slow that when we work with the people at NIST, the basic research people, they actually had to create some new techniques for running tests to determine burning velocity because it was so different from what they're used to. So it was in about 2015 that we realized that we needed to set up a pretty big research program to look at the flammability aspect, since we didn't have good, strong candidates that were non-flammable. And Tom has been running that flammable refrigerant subcommittee all this time. One of the big contributions I think that subcommittee did was to take a survey that was very broad. We sent questionnaires to, I think Tom said, over 100 organizations all around the world, and asked for people to express what they felt like were in gaps where we don't know the answer to a question, but it's important before we start using these refrigerants. And we compiled them, and it kind of collapsed down to something like 60 research requests. And in the equipment category, I think we have like 5 categories. In the equipment category, this research project came out of what was the #1 identified gap. And that is, this is a new category we're not really familiar with how it works. In the past, we've looked at propane back when we were, getting rid of ozone depleting refrigerants. And so as an industry, we have some familiarity with propane, and it's actually used in very small equipment. So we wanted to know what happens if you use A2L refrigerants in typical unitary equipment for air conditioning purposes. And if you cause it to be ignited, what happens? What happens after that? Next slide. Okay, so we were more interested in understanding the severity. The probability of an ignition is kind of a different study. We did learn through this, I guess we internalized the knowledge that it's difficult to ignite this refrigerant, but we were focused on understanding severity. So the experiments were designed so that we were very likely to get ignitions because we wanted to see what happened. We used very high and it's a good rule of thumb to know things like the spark that you get when you walk across the room and touch the electrical switch. That's not a sufficient spark to ignite the refrigerant. And it's been previously established in the standard that are around the contactor of something like a 2-ton, 3-ton air conditioner. That arc that you get when the contactor pulls in is not strong enough arc to light it. So we had to use very high energy. I think there's some ANSI standard for these very high energy sparkers. We used multiple ignition sources around the room, and we placed them in locations where there would be more likely to have an ignition. The refrigerant is, all of these that we're looking at, they're heavier than air. And so the refrigerant, and we used a system for release of refrigerant. We weren't releasing it from equipment that was attempting to hold the refrigerant would be, released from that tank. And the reason that we went that it was very important that we understood what's the leak rate, and we need to have instrumentation to do that. And measuring two-phase flow is very difficult, so we were sending liquid through the meter, and it would flash later, but we did actually see liquid refrigerant that would be on the floor during these tests. And the last thing to say, the scenarios that we're doing, we used as guidance the IEC standard 60335-2-40 as guidance for us, because we wanted to at least be somewhere around what it was thought to be the rules of the game when we got to actually using these refrigerants. And it's good to know the UL standard was actually still in development. It's patterned after the IEC, but the Canina working group can modify to make it more suitable for our market, and they did do that. Okay, I'll turn it back to you guys.
All right, thanks, Dutch.
Thank you. Thank you, Dutch. And George, if I might interject, this is Helen. I just want to let people know that if you have questions, there's a question and answer feature on the internet in a chat. There's also a chat if you have some technical questions for us. Sorry, George, to interrupt, and thank you very much.
Okay, thanks, Helen. Let's go to the next slide. So these reports, both together are more than 900 pages. So I'm going to try and compress everything that's in those reports into about 20 slides. So I'm going to try and talk pretty quickly, but if you want more information, I urge you to go to the AHRI website where those are available to the public. Next slide, please. Okay, so what we're doing is we want to understand the relative risks relative to A1 refrigerants. So we're looking at both A2Ls and A3, and in this case that was propane, and investigate some control limits and safety factors. So let's go to the next slide. And sorry, I look away every once in a while just to make sure I look at my notes page to say everything I want to say. So this is a comparison of the kinds of tests that we did. So we ran the PTAC experiments both with A2Ls and A3. We did a mini split with A3 and a residential AC system. So those were roughly comparable. We did not run a rooftop unit with an A3. You know, the service error is again only done with the A2Ls. So next slide, please. Next slide. Okay. So we started off with some tests in a room that was 8 by 12 by 8 feet high, with an obstruction in it, and in some cases no obstruction. And we did that for the purpose of investigating some very high concentrations within the rooms. So let's go to the next slide. Here's some comparisons. In the top, we have what we call Cal 07, which was an R32 test. And then right below it is a propane test, R290. Both of those resulted in ignitions. They were both released from about 8 inches high, 0.2 meters, at very high flow rates. The concentration, if it had been mixed in the whole room, was about 50%. But when you consider that it's going to mix in a very low portion of the room, so just as an estimate, below 0.6 meters, about 2 feet, you know, we're looking at that concentration, which is 200% of LFL. So that's where we're seeing ignition in those cases, because it did not mix within the whole room. And the same is true regardless of the speed. If you look in the average release rate, you'll see on the top two lines, they're about 13.5 grams per second and 6.8, which are fairly high releases. And in the bottom two, you'll see 79 and 41. Those are just about the size that you'd get from an open-ended 1/4 inch or 1/8 inch inner diameter tube. So pretty significant. Roughly comparable were these other two, where we had a higher release height, and it varied between the experiments, 2.2 meters for the R32 and 1.8 for the propane R290. You know, the whole room experiments, our target concentration was 25%. I just realized I have an error on the slide. At 25% for the whole room on propane, CP21, the below 6.7 or 0.6 meters is a wrong calculation. We did have a slight ignition in that case. Again, comparing higher release rates and lower release rates. So next slide, please. This is just looking at R32, and what you see is we had various things. The label is PbO4 was 50% of the LFL in the whole room, but below 0.6 meters, it's about 200%. So we should get a ignitable concentration. The bottom one, PB12, is also at 50%, and we did not get ignition. The difference is, if you look at this average release rate column, you'll see that our first test, we didn't get the control we wanted on release rate, and it was 62 grams per second. The other two were close to 100 grams per second. And what we saw in the videos is that the higher release rates actually caused very turbulent mixing and did not result in a flammable mixture, where the lower release rate actually resulted in an ignition. And that picture you see to the right there is just showing the example of that R32 flame. And I should point out, you know, there was a high concentration all lower in the room because of the lower burning velocity of R32. The flame was going mostly vertically. It did not spread very much horizontally, simply because the buoyancy effect of the fire was faster than the burning velocity of R32. So next slide, please. This is another example with these high release rates. On the left, you'll see that ignition where it goes mostly upward. The right side, you'll see like a water stain on the floor. That's where we actually had some liquid refrigerant pooling on the floor. We learned, you know, in the propane test to look for that. So take a look at the next slide. This is one of the propane experiments, which is really the same configuration. Again, we're looking at a release that is 50% of LFL in the whole room. It's a low release, and it's impacting on that obstruction, which you can hardly see. So we did get horizontal burning as well as vertical burning. On the right-hand slide, this is an infrared picture where we could see that there was a very cold, I forget, -40 or, you know, -60 degree. Because of the high release rates, there was actual liquid coming out of our discharge tube and pooling on the floor. So next slide, please. This is taking a look at one of the R32 tests. Again, that's about 50% of the LFL in the room. But for safety's sake, we had a open path FTIR that would give us an indication of presence of various gases. So the top picture on the right-hand side is our pre-test picture of the infrared absorption. And in the lower side, it's after the test. And those little spiky fingers you see all the way on the left side are an indication of hydrogen fluoride. So, you know, as expected, we're sensing that, and we used it as a safety monitor that we would not re-enter the laboratory until we saw that spike of hydrogen fluoride go away. So next slide, please. Again, I'm showing here, this is again about 50% of LFL in the whole room, and it's impacting the box as the propane is discharged. We ignite it, and you can see that this fireball is expanding horizontally and vertically and sweeping over the top of the box. Now that box was made of cardboard, and we never had to suppress a fire in that cardboard. So even though we're releasing this at very high flow rates, the duration of that flaming was measured in seconds, in most cases less than 7 seconds. And next slide, please. Now we're taking a look at what we did with some actual air conditioning equipment. So let's go to the next slide. So here is a PTAC with propane, and the simulated break is coming out of the center of the coil and going directly straight into the room. So the grill is actually directing that propane down to the floor. And we have igniters right in front of the PTAC, as well as off to the left. So you'll see that that flame spread pretty quickly. Now, as another safety matter, you can see some windows up there. We actually covered those with plastic as a pressure relief point. We didn't want to have to rebuild our room all the time. And I believe in this case, 2 or 3 of those plastic sheets burst or melted from the flaming. So, and in this case, the unit fan was not operating. So this was an equivalent release about 12% of LFL in the whole room, but again, it shows that it pooled at the bottom of the room. So the next slide. We did a number of tests with A2L refrigerants. Again, slightly different configuration. You notice that the PTAC is located in the center of the room. This was R452B, which still has a significant R32 component. And we were using just a candle as an ignition source. We later learned that candles were not the best ignition source when we're really not trying to deal with the probability or likelihood of an ignition source. That's why you see in the propane series, we used electric arcs that were energized for a number of seconds to make sure that if there was something that could be ignited, it will be ignited. And in this case, the candle did manage not to get blown out, which did happen in some cases by the force of the release. So there was a very small ignition here. We really don't know what would have happened if we were using electric arcs. So next slide, please. So one of the things we wanted to do, we were so concerned about this, in the upper right-hand corner, we moved that PTAC to the side of the room and had the release coming out of the side of the thing so that there'd be a chance for concentration built up in that side of the room. Finally, we used our electric arcs and put it right in front of the release point. And it was coming out so fast that you can see those little blue flames are actually pointing downward, meaning that the sweep of the propane discharge, or the R32, was higher than the buoyancy effect that would ignite. Then the flames were coming up from the floor as unburned R32 met some ignition sources. So, the presence of that electric arcs caused us some problems with the test because it actually interfered with our ability to control the solenoid valve that would shut off refrigerant. So we actually wound up releasing about 1.1 kilograms more of R32, and it was a big mess to clean up. So going on to the next slide for mini splits. So this was with propane, and you can see in the picture on the right that the bottom of that unit is about 1.8 meters above the floor. And when it's operating, the bottom panels open up and the flow comes out of the bottom of that unit and circulates in the room. So we had the map on the left shows we had an arc location immediately below it and scattered at different places around the room. So that's what we were doing for mini split testing. So next slide, please. This is some of the results we had. And the thing to concentrate on is the planned discharge or the actual discharge. The first one is 327 grams. We actually did 2 tests. The first test was without an ignition source, just so we could measure what concentrations we were seeing. And the LFL for propane is about 2.1%. So in every case of these pre-tests, we did see that we had flammable mixtures that could be ignited. Then followed up with those were ignition tests. We had 6 deflagration vents in the room. So with the fan state off, meaning there's no air circulation, 320 329 grams, is about 18% of LFL in the whole room. And we did get ignition. It did burst about 5 of our vents and melted one of the others. So all 6 vents eventually opened. The next we went to 114 grams, which was only 6% of LFL if it was scattered throughout the room. But there was still enough to ignite. It was a little less energetic. We burst 2 of the vents and 1 of them was melted. Going to a higher discharge, but in this case with the fan on, running continuously before the discharge, we had a discharge of 650 grams, which was 36% of LFL in the whole room if evenly distributed. We did see a concentration of 2.8%, but possibly due to different locations of the electric arc, we did not see an ignition with the air circulation. Finally, at 650 grams, we did a little test to simulate what might happen if we had a refrigerant sensor embedded in the unit that triggered some action, mitigating action, to start circulating air in case a leak was detected. And in this case, the order to start the fan was delayed by 15 seconds after the release was started. We did get an ignition at a very different location instead of immediately under it. So the fan had started to sweep away a lot of that propane concentration, but it took about 10 seconds for that fan to fully deploy and come up to full speed. So I think if the fan had had another 5 seconds perhaps, and this is just supposition, it's possible that it could have swept away any possibility of ignition. And finally, we did not test the 975 grams because we did have an ignition, at the 468 grams. So next slide, please. So this is again the propane ignition with no air circulation, showing it's spreading vertically and horizontally. The next slide. We don't have an analog to the mini split for the AC application. And so we're using this residential unit, which was vertically mounted, simulating a leak in the A coil. And where you see that black printing, ignition occurred before, the fan was not operating when the leak was started. So what happened is it was falling out of the bottom of the unit and into the hallway where we had candle ignition sources and electric arcs. And again, simulating some mitigating action, the blower was going to be turned on 30 seconds after the start of a release, meaning that something could sense and do that. In this case, the delay time and perhaps even the roll-up time for the fan was not sufficient to stop ignition. And so what happened when the fan did start, it pulled that flame out of the hallway back into the ductwork and was blowing the smoke products out through the supply. So next slide, please. We looked at a rooftop unit with R32. This was a 14 by 16 by 8 foot room, so it wasn't a full size kitchen unit. So we had adjusted the charge size to release within the rooftop unit. What happened is the charge was, when we released that charge, if it had all gone on to this simulated kitchen, it would be about 75% of LFL in the room. But in this case, we started the fan sometime after the release, and I don't have that in my notes. I know it's in the report. But what happened is you can see this mist above that center countertop that's coming out, And in many cases, again, because we were using candle sources and not, gas burners, we don't know if there was a mixture that could have been ignited. The data we collected didn't show flammable mixtures. So, that's about the only kind of a data point that we can get on that. If we look to the next slide, okay, this was looking at a servicing error where, it's charged or something and a line comes loose. So what we had was a little fixture here where we had 2 lit candles and an electric spark igniter, and then that refrigerant would blow straight across the candles and across the igniter. So with R410A, with this particular setup, and again, a very high flow rate, we did not get an ignition. There was lubricating oil, but we did get an ignition with both R32 and R452B. So take a look at the next slide. This is taking a look at the trailing edge of the R32 experiment, and you can see a little blue flame, exiting from that discharge location. What happened earlier in the test were these very high flow rates of 45 grams per second. That's what the chart is showing. It was essentially blowing off the flame. So we had some, the candles were blown out immediately. The candle on the floor stayed ignited. And then the electric arc came on and was doing some combustion, but the discharge rate was so high. Once it tailed off, this is probably down to around 2 grams per second at the end of that. The flow was low enough that there was some ignition extending a few inches beyond that ignition point. So some of the work we're going to be doing in the firefighter project that I'll talk about some other session is to look at what would happen if that ignition source were at some other place in the room that perhaps wasn't going to cause a flame blow off. So we don't have in this particular study any of those kinds of results. So that's really my last slide. I had another slide that just talked about some of the refrigerant properties, but we can pass on that. So I hope I'm within my time limit now, Helen.
Thank you so much, George. That's fantastic. We really appreciate this. And I know that everyone, over 400 people on the line are very interested in this. There have been a couple of questions about whether or not the webinar will be available. It will be recorded and it will be available on our website. So if you have interest in seeing it again or passing it to other folks, it will be available there. Viral, let's hear from you now. Thank you.
All right.
Excuse me. Sorry, Viral. Sorry, we're allowed to chat now. We'll have a couple of minutes for this. So Dutch and Rusty, thank you so much for participating in this. Wanted to talk with you a little bit about the learnings from this testing. So if you could kind of speak with us a little bit about what we learned from all the testing that was done with UL in these early days, that would be very, very helpful.
Sure, I'd be happy to. And I'm reminded that I need to set up Viral's presentation also, so don't let me forget that. So we felt like we learned quite a bit from the 9007. And, if we were to go back and do it over, we would do a lot of it differently, but that's the way things are when you're learning. In the very beginning of the program, the first sets of tests, if you pull down the report, you'll see we were doing, what they call design of experiment, because we didn't know things like what's the effect of humidity, we literally ran, the same test over with lower humidity and higher humidity. We didn't, the way the standards have been written, you use the floor area of the room and some height, the release height, to calculate basically what is considered to be the volume of the room. And then you use a safety factor so that you don't get a mixture that's some percentage of the lower flammability limit. So it was really good for us to learn that indeed, if you drop refrigerant from the ceiling, like in that rooftop unit, the return and the supply were both in the ceiling. We actually didn't get ignitions, and the reason was because just the refrigerant falling through the air mixes it up enough that you don't get a combustible mixture. One of the things I guess is good to be aware of is the working group working on the UL version of the standard used a different lower allowable percentage of LFL. The idea was to build in some extra safety factor because those averages are what maybe the final state would be, but from the beginning, the leak is concentrated in a certain part of the room. So even though you wouldn't have a combustible mixture after some time period, at the very beginning, if there happens to be an ignition source near where the leak is, then you could still have a ignition. And another change that we did with the standard was having a faster sensor response time. It's just another attempt to be more conservative. We changed it to, there's a sequence of timings that add up, but we required a faster response time compared to the IEC version of the standard. George mentioned the high velocity leaks. They also tend to mix with air. So you get rapid dilution. And one of the other things that we were looking at was what's the effect of having obstructions in the room, because they're not actually taken into account. For instance, if you had a convenience store, all of the shelves that are stocked with goods, those are not taken into consideration when calculating the maximum charge. And so we wanted to be able to explore if you have an obstruction, furniture and so forth, can we document the difference that it makes? And we were able to do that. So Rusty, any other things come to mind?
Dutch, you did, as usual, you did a fantastic job addressing those issues. And I guess a simple response is that there were a variety of changes that were implemented into the safety standards, both UL/CSA 60335-2-40, as well as AHRI 15, as a result of these projects. And one of the bigger ones, as Dutch mentioned, is the reduction in response time. So it is the requirements that are in UL 2-40 as well as in AHRI 15 are more stringent than what is in the international safety standards for the similar products. So we are here in the US, based on this testing, we've modified our requirements for those. One of the things I would like to comment on is, as shown on the screen right now, as far as the various A2Ls, one of the questions that was asked was, why didn't we include R454B in this series of testing. And my response to that is that 54B was not considered to be one of the primary candidates when the testing was beginning. But the reality is, as the testing shows, is that there's not a wide variety of difference between the 52B and 32B based upon the properties that are defined in ASHRAE 34. We would not expect a major difference between any of the A2L candidates. But what we do see is that there's a very significant difference between the A2Ls and the A3s, such as R20. Going a little bit further, with any of these refrigerants, one of the things you see with the combustion, actually regardless of whether it's an A1, like the R410A or R22 that's used today, or these A2Ls, some of the combustion byproducts is HF. So all fluorinated refrigerants will have the HF as a combustion byproduct. And there's other refrigerants that might have other combustion byproducts, such as hydrogen iodide, that we need to be mindful of also. So the simple fact is in ASHRAE 15 and 2-40, we did make measurable changes to the requirements based upon this particular testing. Alan, back to you.
Oh, well,
Thank you, Russell.
let me introduce
Doug.
Raul. So one of the major findings from the 9007 project was that the way we were releasing refrigerant for these tests was not really the way it happens in real life. And we realized that we really needed to get to the bottom of that. So we actually created a new research project, 9012, which was done at Oak Ridge National Lab. And the idea behind it was for us to use literally the equipment that the refrigerant would be released from, and we would do these over and over again, where we would have the leak come from running, in another case with the compressor off, then have the leak from the high side with the compressor running and with the compressor off. And we wanted to get very good documentation of what is the characteristic of leaks from equipment under these realistic scenarios. And, you know, a takeaway from that is when you have a leak from an air conditioning system, regardless of whether it's running or not, there's a couple of things that happen. First, the pressure driving the release drops through the release. So the highest flow rates are at the start. Another thing that happens is because of the pressure reduction inside the system, the refrigerant chills and the heat exchangers that are in there chill. And that tends to prevent complete loss of refrigerant from the system, because it actually gets so cold in there, the refrigerant's happy to stay in there for a while. So this was, you know, we wish we had known this before we started our 9007 test, but Viral is going to go through the testing that they did and show you this stuff.
All right. Thank you, Dutch, for that introduction. So this is an outline of the talk. So I'll give an overview of the project and the objectives. I'll talk about the general approach for the air conditioning equipment that we tested. And then I'll talk about the results for the multi-split AC system, along with the test plan for the ducted split heat pump system that we are about to test. And then I'll conclude at the end. Next slide, please. So the overview of the project is that this is a test program to document the dynamics of real-life refrigerant leak events in air conditioning equipment. Phase 1 of this project involved 5 systems for air conditioning and refrigeration. And we reported these during the UL meeting in October of 2018. And there are a couple of publicly available reports available as well. For the phase 2 results, which I'm going to talk about today, we are looking at 2 additional systems. So the idea is to conduct refrigerant leak testing under a controlled environment, as Dutch said, we've come up with a sort of standardized test method with video recording and measurements of refrigerant concentration, temperature, pressure decay, mass flow rate, and oil loss. We have set requirements for the ambient temperatures and other conditions such as steady state conditions. In this case, we used refrigerant R410A for all tests. And the table at the bottom just kind of shows you the different scenarios that we studied. I'll go into a bit more detail about what we mean when we say we looked at different leak rates and leak locations and equipment states. Next slide, please. So the objective of this project is to conduct refrigerant leak testing on air conditioning equipment under real life conditions. We measured the system pressure decay rate and mass flow rate of the leaking refrigerant, and I'll show you how we did that. And of course, we also measured the volume concentration of the refrigerant. In this case, we used oxygen concentration sensors to indirectly measure the refrigerant concentration. So as the refrigerant was released, it displaced oxygen, the O2 concentration went down, and we assumed that that's how the refrigerant concentration went up. For the phase 2 project leak rates, we controlled the leak rates using 2 different orifices. One was a larger 2.7 millimeter orifice, which resulted in a 3 to 6 minute release time, which is the same order as a reasonable worst case 4-minute leak that is specified in some safety standards. And then we studied the smaller leaks, which resulted in 15 to 25 minute release times, which are more indicative of actual leaks. So compared to the phase 1 tests that we did, the phase 1 tests involved full bore leaks. So they involved essentially a catastrophic leak event and a much larger release of refrigerant in a very short time, whereas the phase 2 leak rates were focused more on things that you might actually have experienced in actual applications. Next slide, please. So I'll talk about the general approach. So these are the 2 pieces of equipment for the phase 2 tests. On the left is a multi-split AC, and on the right is a ducted split heat pump. You can see the schematics of the vapor compression cycles at the bottom there, and what we call low side and high side leaks. So for the split heat pump, you can see that when we say high side, we are releasing refrigerant at the exit of the condenser before the expansion device, since the expansion devices are part of the indoor unit. So it is a true high side leak. And then of course the low side is on the suction side of the compressor. For the multi-split AC, we still use the same terminology, but you can see that the expansion devices were actually part of the outdoor unit. So really the difference between the high side and the low side leak is the pressure difference across the evaporator. Next slide, please. So this is a schematic of the test setup for the multi-split AC. We tested them in the environmental chambers here at Oak Ridge National Lab. We have an outdoor chamber and 2 indoor chambers, and we had 2 indoor units. On one of the indoor units, we installed a refrigerant release mechanism, which is a pneumatically actuated valve. We have the oxygen concentration sensor trees you can see there. And then we also had a leak release pan that was used to capture any oil that was released during the leak event. And in all of these cases, for the multi-split AC, the system charge was 1.75 kilograms. Next slide, please. We also performed tests in a smaller room. So for this system charge of 1.75 kilograms, if you go to the appropriate standard, you can use that charge to calculate the minimum room area. And so what we did is we created a room with a false wall, and we were able to conduct tests in what we call a small room or a room with reduced area. Next slide, please. So these are some of the test results. The detailed results are available in the supplemental slides. I just wanted to go over the test matrix really quickly here. So again, for the large room and the small room, we had identical test matrices. We had low leak rates and high leak rates, which, as I said, were controlled using the different orifice diameters. We had tests with the equipment on and with the equipment off. When the equipment was on, that means everything is on. So the compressor was on and all the fans are on, including the fans on the indoor units that are responsible for recirculating the air. And then, as I mentioned on the previous slide, we have a low side and high side leak. Next slide, please. So these are some of the typical test results for the multi-split AC. The top row of graphs are for the large room test, and the bottom row of graphs are for the small room. These are all tests with a 1 millimeter orifice, so it's a low leak rate. The tests were conducted with the system off, and the leak location was on the high side. The first graphs show you how the system pressures decayed with time after the leak event, which is denoted by the dotted line. And so you can see a very rapid decay in the system pressure down to atmospheric pressure. The second graphs show the charge release as a percent of the total system charge, which was again 1.75 kilograms. And then finally, we see the power consumption. In this case, since the unit was off, the power consumption is 0. However, you can notice that it was in fact running before the leak. And so we did this to essentially try and replicate a real life scenario where equipment has been running and then it has been turned off. And so refrigerant is sort of distributed. Next slide, please. Concentration sensor trees are laid out to scale, but you can kind of see how far away things are from the leak release point and the different heights at which the sensors are installed. One thing of note here is that big blue arrow is used to illustrate the airflow coming out of one of the indoor unit when it is operating. So in air conditioning mode, of course, the system is running and the fan is blowing cold air over our sensors. And we found out that, in fact, our sensors are quite sensitive to temperature. And when you have sort of non-uniform temperature, it can affect the measurements. And I'll talk a little bit about that. Next slide, please. So these are some of the concentration measurement data for the tests. These are, again, the same tests that were shown a couple of slides ago. So the top row are for the large room release with a small orifice. Bottom row is for the small room, small orifice. The graphs on the left are showing the raw oxygen concentration data. And then the middle graphs and the ones on the right are showing the R410A concentration. They're showing the same thing. It's just that the ones on the right are zoomed in a little bit. So immediately you can tell that for the small room case, the maximum concentration peaks at about 5.5% volume concentration, which is about 38% of the R32 LFL. The peak occurs about 17 minutes after release. For the large room, we see that the maximum concentration is about half, and it's about 17% of the R32 LFL. And the peak also occurs about 20 minutes after release. Next slide, please. Here we're looking at tests with the larger orifice. So this is what we call a high leak rate. And here, I guess the clear difference compared to the previous results are how quickly the peaks are reached. We are still reaching peaks of about 5%, 5.25%, for example, for the small room, but it occurs much, much faster in about 5 minutes. For the large room, we get to about a concentration of 3.4% or 24% of the R32 LFL, and this occurs about 2 minutes after release. Next slide, please. So here we're looking at results for the test with the equipment running. And again, the leaks are from the high side. In this case, you can see that the refrigerant concentration peaks are much lower compared to the unit off tests. We're getting up to between 2 to 3% for the large and small rooms respectively. However, as I mentioned, we did have some issues with the concentration sensors being affected by that cold air that was blowing over the sensors. And so what we have to do is we have to actually calibrate or correct these results so that we don't see these kind of negative concentrations that you can see in the graphs on the right there, or sorry, in the middle. Thank you. So this is a summary of the multi-split AC results. We saw maximum concentrations of 3.4% in the large room and 5.5% in the small room. We considered the raw data for the unit off tests to be good and reliable because the temperature was fairly uniform in the vicinity of the sensors. But for the on tests, as I mentioned earlier, because of the temperature sensitivity, we'll have to do some calibrations and additional signal processing to normalize these effects. In terms of the release times, we did not see any clearly discernible difference between the large room and small room tests. The thing that had the biggest impact, or the most obvious impact, was the leak orifice size. So with the larger orifices, we released refrigerant in a much shorter time, and so we had a lower release time as a result. Next slide, please. So I'll just go over the test plan for the split heat pump. So as I mentioned earlier, it's a ducted split heat pump system that we're going to test. It can operate in heating and AC modes, so we'll be doing both modes. The nameplate charge for this system that we have is 3.83 kilograms. However, again, when we look at the appropriate standards for the room size that we will be testing this in, we determined that the maximum charge is up to 5.7 kilograms. And so that's one of the charge levels we're going to test to. And the way we achieve this increased charge is to use longer connecting line sets. In this case, we'll use a 127-foot connecting line set to raise the system charge. We'll conduct 32 tests for 2 duct systems. The first is we're going to mimic an attic air handler and supply duct location with downflow registers, and I'll show you a couple of schematics of that. The second is we'll mimic a closet air handler on the first floor with attic supply ducts and vertical downflow registers. We also plan to track oil loss as best we can using a sight glass that's installed on the compressor. In terms of the leak release point, it is going to be inside the air handler unit, and we're trying to get it as close as possible to being near a braze joint on the coil header. We are equipping it with a diffuser, which I'll show you in a few slides. So this is a schematic of the duct system 1. This is an attic air handler, and you can see that the outdoor unit is installed in the outdoor chamber. We have the connecting lines, and we have a stand that's about 8 feet high, and we have the indoor unit installed on that. And we have the ductwork as shown in the diagram. We'll have concentration sensors at the outlets of the supply diffusers, and then we'll also have them arrayed throughout the space. And the refrigerant release mechanism will be installed on the in the air handler unit. Next slide, please. So this is the system 2 schematic. So in this case, we will build a temporary closet enclosure around the air handler unit. And again, we'll have concentration measurements arrayed throughout the space, and everything else will be the same. These are just some of the photos of the current fabrication that's taking place. So we have the ductwork laid out in our environmental chamber, and you can see the air handler unit. This is the attic install, and you can see the air handler unit installed on a wooden stand up there. At the bottom are a couple of photos showing the leak release control valve. So it's installed outside the unit just because of space considerations, but the leak is actually going to be occurring inside the unit in between this heat exchanger and you can see the photo of the leak diffuser. So the leak will occur and then it will be sort of, the fluid will pass through that shower head looking thing that you see there. And we'll have a leak viewing window so we can also capture our video. Yeah, I'll just go over the conclusions here. So as mentioned earlier, this work was sponsored by the DOE Building Technologies Office, and this was a collaboration with AHRI. It was an experimental study on refrigerant leak characteristics. The objectives, which were to conduct refrigerant leak testing under real-life conditions and to document pressure decay and mass flow rate, were met. We have completed testing for the multi-split AC. The ducted split system AC remains. In terms of concentration data, as I mentioned earlier, we got to these kinds of maximum values for the low and high leak rates. And these were all for the unit off tests with no air circulation. We also have the data for the unit on tests in the supplemental slides. We also have video data, which I did not show here today, but we're capturing video from many different angles to observe the leaks. And we will summarize all of these results in a final report, which will be submitted to DOE and the RD Project Monitoring Subcommittee for review before it will be publicly disseminated. I think I have one more slide on acknowledgements. So as I said, this is sponsored by the DOE BTO. I'd like to also acknowledge the RD Project Monitoring Subcommittee for their very helpful comments, donation of test equipment, and general guidance throughout this project. And of course, the contributions of my colleagues at ORNL, Maud Abuhiba, Jeffrey Chambers, and Van Baxter. And I think that's it.
Well, thank you very much. Really appreciate that. And we're going to next turn to Dick Lord to talk about some work that he has done around application testing. Thank you, Dick.
All right, good. Yeah, thank you. I'll be the last presenter. So what I want to, like to go to the next slide. I want to talk about some application testing that we have done at Carrier. So two areas I'm going to focus on. One is electric heat, and you can see the typical electric heat that goes in a residential and commercial unit where the air blows over the heater. And then the second one is talk about some testing that we did with a fan coil located in a closet with a water heater, and the water heater has a standing pilot. So next slide, Helen. So the electric heat testing, you can see, yep, we'll just go right to the slide. So the electric heat testing, one of the areas of concern that we had was that electric heat can actually exceed hot surface temperatures. And we haven't talked about it in this session, but we have in some of the other AHRI webinars. One of the things we found with these A2L refrigerants is they don't burn when you expose them to their auto ignition temperature. So we developed over time, and that was an AHRI project 9008. We developed what we call a hot surface test procedure. And the test procedure basically blows a flammable mixture of refrigerant onto a plate, and then we see if it ignites. And that's all defined in project 9008. It was then basically wrapped into Annex KK in the IEC standard as well as the UL standard. And basically what we found out is that the temperature is much higher where these A2L refrigerants can ignite. So we expose them to a plate at 860 degrees. We see if it ignites. If it ignites, and we keep dropping it at 20 degrees C temperatures until there is no ignition. And typically we find most of these refrigerants are around a 700 degrees C limit. But the concern we had with electric heaters is not normally in operation, but in extreme conditions where they're low on airflow, where the fan may fail, they can exceed 700 degrees C temperatures. So when you can see a typical electric heater that is running with very, very low airflow and very, very high watt densities, you can see it's glowing pretty high temperatures, well above 700 degrees C. So let's go to the next slide, Helen. So what we did is there was a lot of theories that A2L refrigerants, because of their low burning velocity and difficulty to ignite, some of the stuff which George showed in his presentations, that they would not ignite in moving air. But there was no research plan to do that. So we said, let's build a test rig and see if we can do this. So we took a typical residential fan coil. We took our smallest unit, which is a 1.5 ton unit. We put an electric heater in it, and it was lucky that I could put an oversized electric heater in. That unit's limited to 10 kW, but I put a 15 kW heater in it. And so that's a very, very high watt density. It's limited to about 775 CFM, and we'll run it well below that CFM, as you will see. And so we measured the surface of the electric heater, put thermocouples on the heater, then we calibrated with an infrared camera, and then we also measured for presence of HF. There was some concern that even if there was not an ignition, the high temperatures of the heater would gradually break down the refrigerant and make HF. Next slide. So this is the test setup. I won't dive into the detail. I just want to point out a couple of things. Up in the left-hand corner, you can see the electric heat, and there's basically a visual camera shining down through a window. And then we had an infrared camera going through a special optical window to look directly at the surface of the heater so we could get the temperatures. Then we had a leak site, very similar to what was just shown, where we used an orifice to feed the refrigerant into the evaporator coil. So and basically on the side where it would go through the evaporator coil, then through the fan, then hit the electric heat. And that's the way most units are developed. So I won't spend a lot of time looking at the slide, just in there in case you want to look at it. So a little bit of just grounding on refrigerant. So we were going to test R32, and if we had an ignition, we would test with 452B, which is a little lower burning velocity. And Rusty talked a little bit about those two refrigerants. So if you look at a typical LFL for a refrigerant like R32, it's 14.4% LFL by volume. The upper limit is where it becomes non-combustible again, and all refrigerants have a range, is about 29%. So we targeted to get to what we call a stoichiometric mixture, which is about halfway in between this. So we basically targeted to get a significant leak while the fan was on. So what we did, and this is basically the outline, we'd start the fan, we'd bring the heater up to temperature, make sure it's stable, start our instrumentation, and then introduce our leak rate and see if we got any ignitions or if we formed any HF. So next slide. So this is the results of the test. And what I did is and you guys can look at this later if you want, but we showed the leak rates, and we had to have significant leak rates, you know, in the order of 18 to 15 pounds a minute. That's well beyond the charge that this unit has. This unit would only have about 5 to 6 pounds. You can see the leaving air temperatures, you know, we started getting well into extremes. You know, the limit by NFPA 90 is 200 degree leaving air temperatures. We were running temperatures up to 425 degrees. So you don't see those in real life situations. They're just not approved by code. You can see our standard airflow. We HVAC designers tend to think of CFM per ton. So we're, you know, typically units are run around 300 to 400 CFM per ton. All electric heaters have a limit. You can see we were running CFMs per ton down into 130, 117, down as low as 84. That's well outside the range. And you can see the max infrared temperature that recorded temperatures well above the 700 degrees C. So this was very, very extreme testing to see if we could get an ignition. Next slide. And bottom line, we got no ignition, but I'll get into the details. So I'm just going to run through these quickly. I'll just show you how the heater warms up. So on the, you know, test number 2, that's outside the normal operating range. You can see the heater starting to get red. See the infrared at the bottom. We changed filters on this so we can actually measure these temperatures, and we back it out through our software. And then you can see test 3 gets a little bit warmer. Our heater temperature is now 736 degrees, leaving air temperatures outside the limit. Test 4 getting warmer. Next slide. Sit on. Getting a little warmer. Now you can see these heaters starting to get to glow. I put up in the left-hand corner heaters. You know, you can actually tell the temperature heater just looking by the color. So, you know, you can see the typical color scale over on the right-hand side. You can see it starting to get up into the lemon yellow, and how good your color rendition is, and white hot. You know, that's it. You can see some of these temperatures getting very, very warm. You can actually see we had a special high temperature optical clear plastic that we were using, and it's starting to deform this plastic because it was getting so warm inside that heat exchanger. Next slide. You know, test 8 getting warmer, test 9 getting even warmer, test 10, and we'll concentrate on test 10. Test 10 is where they'll dive into some of the details. Next slide. Oh, and just one thing I'll show you, we actually were able to catch a failure. We ran this heater so hot that we finally shorted out some wires, and you can see on the right-hand side, it's actually arcing and failing the heater. So, and then the safeties tripped it off. And one thing to note on this unit, we had most of the safeties overridden. There's typically 3 limit switches on these that are a UL qualification test. Those are all jumper. They all would have tripped long before we got into any of these temperatures. Next slide. So here's the result. So this is test 10. This is a pretty severe test, R32. Voltage is up at 240 volts, or running 15 kW or 14.4 kW. You can see the airflow is down to 115 CFM, 164 CFM per ton. Leaving air temperature up at 327, well outside the UL operating range. Heater temperature up at 927 degrees C. And then we ran a 60-minute leak, and we had to leak 15.8 pounds. So that's a significant charge. And what you'll see happen on it is, it's kind of interesting, is, you know, at 10 seconds, we turn on the leak. The heater's up to temperature, 1700 degrees. You can see immediately it starts to quench that heater. We're essentially leaking 5.5 tons of capacity. So we're cooling that heater down, and you can see the heater temperature drop. It drops down during the leak test, and then it starts to rise up after the leak test. We had no ignition during this period, and you can actually, you can see the heater temperature drop as you go down through the test as to what happens. Next slide. I put this slide in there because we get a lot of questions about, well, what's a leak look like? So this is a kind of a snapshot. We recorded the leak during the test, and you can see heater up in the left-hand corner. You can see the orifice. You can see where it impinged it on the coil. It actually bent the fins because it's such a high force. And you can see at time seconds 9.7, you can see the leak starting to form. You're not seeing refrigerant. What you are seeing is moisture in the air condensing out. This was in San Antonio. It was actually a relatively dry day when we ran this test, but this refrigerant boils at minus 61 degrees F. So it condenses the moisture out of the air. And you can see as you progress along in the leak, it gets bigger and bigger. You see more and more moisture coming out. You actually see down in the bottom pictures, we turn the coil into a thermal storage device. It actually freezes all the moisture out of the air, and it embeds ice in the coil. If you were to listen to this, and sometime if we ever get a face-to-face, we recorded the sound during this test, and the baseline unit was running at about 46 dBA without the fan on. You turn the fan on, it goes up to about 52. When you turn the leak, it goes up to 76 dBA. Now, those you don't think in dBA, that's 8 times louder than the fan, and we were standing outside, or the camera was standing outside the unit. So this is a very audible leak. It sounds very much like a compressed air leak if you were to vent compressed air. So it's a very noticeable leak. So HF generation, we know A1s and A2Ls, when they are ignited, they'll make hydrofluoric acid. And we check this unit for the presence of HF. And, just as a reference, R32 has an auto ignition temperature of 648, about 1100 degrees. So we're above the auto ignition temperature of that refrigerant. We did not measure any HF. We had a very, very expensive FTIR measurement system that could measure the concentrations of 32 and HF. Did not measure any. We actually went into the test after each test, and we probed the unit for any presence of HF, including the heaters. We did not measure any HF at all formed during the testing. Next slide. So summary, we confirmed that basically when you have airflow in very extreme temperatures on electric heat, you do not get ignition. Now, there has been other tests in the industry. If there's no airflow, you will ignite the refrigerants. So, we went well above the 700 degree hot surface temperature, and we found, several attributes that kind of make this self-limiting. The leak rate to get enough flammable mass, keeping in mind, HO refrigerants at a very high concentration, actually quenches the heater. It cools it right down. We had to leak more refrigerant than the unit has in its system to leak the charge. And you saw, as Viral just showed, that, this was a constant leak, and it's going to degrade very, very quickly because of pressure. And then last of all, we confirmed there was no HF generated, well above the auto ignition temperature. Next slide. So we took this data and we fed it to AHRI 15. I'm not going to dive into the details, so we set it to ASHRAE 15. They updated their standard. I put the actual clause in there, 7.6.3.3, which says, hey, you can exceed hot surface temperatures as long as you have minimum airflow. They used the 200 feet per minute. We did the same thing with 2-40. They took a little different path. They put a Q-min CFM. They're very equivalent, and those CFMs are well below where heaters would really run. They're still well above where I ran them. So they're basically a safety mechanism that we built into the standards. Next slide. So last thing I want to talk about, there's a lot of things that were brought up in some of the code hearings about, well, what if I have a water heater in a closet next to my air conditioning unit and I get a leak and the leak leaks into where the pilot's at. So you can see typical applications. Some of these are not code compliant because they're supposed to have louvers in the doors, but these are what I found on the internet. And so we basically created a test setup like this, and you can see our test setup there. We did this in Southwest Research. We basically took a typical water heater and we removed the flame arrestor. If you guys are familiar with water heater standards, as of 2004, they have a flame arrestor in them that basically prevents flashback of gasoline fumes. So if you have your water heater in the garage and you're cleaning something with gasoline, it won't flash back. It'll go up the stack of the water heater. So they actually have to run a test. So we moved that flame arrestor, and then we created a flammable mass around that water heater, keeping in mind that this has also been addressed by 2-40. Basically, 2-40 says you have to put in specific designs that prevent a leak from the refrigerant piping into that closet. So you either have to have your joint inside the water heater, or you have to have a specially qualified ISO 14903 joint that's used on the fan coil to protect it. But we said, all right, somebody ruptures that line, let's see what happens. Let's go to the next slide. So we ran this test, and we ran 3 different refrigerants. We ran R32, which is an A2L, ran 1234ZE, which is a very, very low flammability A2L, borderline flammable. It's actually non-flammable at room temperature, but we were running this in high humidity, and it does become flammable with those conditions. And then we ran 410A as a base refrigerant, which is an A1. You can see on the left-hand side, there's the pilot, just barely can see it through the window. You can see 410A, it actually ignites and it extends the flame. It does generate HF. We measured HF going up the stack, no HF outside the units, no flashback out of the unit. So, you know, keeping in mind A1 does not mean non-flammable. It just has no propagation of the flame during the ASHRAE 34 test. So then we ran ZE, and it's kind of interesting, ZE being the least flammable refrigerant shows the more flame extension than any of the refrigerants. And then we ran R32 over on the right-hand side. You can see it generated similar ppm levels of HF at about 70 ppm. So, you know, we basically confirmed that even if you have a stoichiometric mixture outside a water heater, it's a pre-2004, it's really not a risk that you would get a flashback out of the water heater. Now the combustion would go up the stack. So with that, I'll stop and turn it back over to Helen.
Thank you, Dick, and thank you everyone for your presentations. We don't have a lot of time. We're actually out of time, but we'll try to answer a couple of questions, and then we'll go ahead and wrap up. And I did want to say, again, this presentation will be online. We'll try to send a link out to folks that are interested. If you have questions that we don't get to, if you want to send them to us by email, we'll be happy to try to get an answer back out to you. And I'm so sorry that we can't cover all the questions that we've received. The first thing I wanted to touch base, Dutch, with you on, I thought it was very interesting that you talked about the first testing that was done in the context of the IEC work. And so it almost sounds like the testing was designed to model sort of the parameters included in the IEC standard. Could you talk a little bit more about that?
Yeah, that's right. It was. And the reason is the way the standards under this harmonized system work is there's an international standard that's developed first with participation from lots of countries. And then regions can adapt it to what they feel their needs are. And so the UL version, there was a group that was working on developing what would be our version of 60335-2-40, but they were still trying to make decisions. And so naturally we would start with what the IEC has as a baseline. Does that answer that?
Yes, very well. Thank you very much, Dutch. And so Rusty, as we kind of learned all this new information, I know, you chair AHRI 15 and you're very much involved with the safety standards. So as we learned all this new information, we talked a little bit before about how this was incorporated in the standards. So one of the questions that we've received is around how does LFL work, right? So the lower flammability limit, the LFL, we saw some testing where there was a 25% of the LFL with no ignition. In some cases, when there was just 50% of the LFL, there was some ignition occurring. And can you kind of talk about, refrigerant density and kind of explain that a little bit to help folks understand that?
Sure. Thank you for asking. The LFL, as you mentioned, is a refrigerant charge quantity per unit volume. So it's either pounds per cubic feet or kilograms per cubic meter is the LFL. And based upon the testing that is done for getting a refrigerant listed in AHRI 34, some fairly accurate values are determined for the LFL values. And the requirements that are in AHRI 15, proposed requirements in AHRI 15.2, and UL/CSA 2-40, those restrict the percentage of LFL, depending upon the application, to a value low enough that you would not typically get to the actual LFL within the space. So we utilize the LFL and a safety factor to get to a safe application. Hopefully that answers the question, Helen.
That's very helpful. I think the other question, I'm not sure whether Dutch or Rusty should answer this one, but or George even, when we looked at some of the testing, there were obstacles placed around the room, and I think we've seen some questions from the listeners around, what does that mean? Was that taken into account in the standards? We did see obstacles in some of the testing that George showed us earlier. And so how is that taken into account from an overall LFL perspective, or kind of making sure that the standards there wouldn't be issues created due to obstacles in the room? Maybe Rusty, maybe you would want to jump in and answer this since we only have a minute or two left.
Thank you. Thank you, Helen. So the reality, yes. So the one thing that everyone needs to bear in mind as you consider those task 1 or phase 1 tests from 9007-01 is that the concentration listed was utilized was actually a whole room concentration, and that's not what's allowed by the 2-40 standard. And so therefore, with the lower percentage of LFL that is allowed, that helps to ensure that even if there are space, as Dutch mentioned earlier, if there are things in the room that take up space where the refrigerant cannot emit to, as well as if there's not a continuous mixing where the refrigerant air is mixed very well, the safety factor is utilized to make sure that you stay below the LFL in those areas.
Thank you so much, Rusty. And I am so sorry, we're out of time. We do have a couple more questions. Again, if you'll send us an email with your email address, we're happy to try to provide answers to you around any of the questions that we were unable to address in this short period of time. We do have other sessions. We got a session every week in the coming weeks. So the next one will start at 11 a.m. Eastern Daylight Time. And we do hope that you'll join us. Finally, I do want to thank all the speakers. You're seeing just a very teeny bit of the work that they've done around trying to support the safe transition to low global warming potential refrigerants as regulations come into effect that all the equipment manufacturers have to comply with. So thank you all very much, and thank you for joining us today. We are happy to have so many people, over 400 people, attend the session, and we look forward to your attendance at the next one as well. Thank you.